Okay, today we're talking about comparing data, and there are a couple of gotchas. There's at least one gotcha on this that I will illustrate, and then we're going to talk about the while statement. So having the basic flow control facilities at your fingertips is an important thing, no matter what language you're using. Each language is a little bit different in terms of how they do things. So for example, today we're going to talk about the while statement, and then tomorrow we're going to talk about the do while statement. And the thing is that there's another construct that some other languages have, and that's called the repeat until, and that's kind of the flip of the do while. And what Java decided when they were first being developed was they wanted things to be simple. So some of these constructs are in a way overlapping of each other. In other words, if you have specifically the repeat until and the do while, one can be written in terms of the other. So if you have the do while and you want to do a repeat until, you can do that. It just, you have to flip things a little bit. So they decided just to not have the repeat until, for the objective of keeping the language small and simple. And of course, in the intervening years, the language has gotten large and complex. So how's that working for you? Okay, so some of the key things, we're going to start talking about comparing data, because when we're looking at these flow of control things, like we've seen the if and the if else, we're talking about the while here. There are Boolean conditions for that. And especially when you combine it with ifs, it's important to understand what the best way to compare things are. And the first gotcha on this is floating point double equals. So we've seen the double equals is useful in some contexts, and it's important to understand when it is not useful. It is useful when there is an well, I'll be getting into that a little bit more. Okay, so if you bottom line, do not use double equal for comparing two floating point numbers, whether they're floats, which we will not use here, or doubles, as we will use here. Double equals is not useful, and I'll show you why, and show you the alternative. And so with floating point values, you don't want to say, are they equal? Because that will inevitably be false, even if they ought to be equal. The question instead is, are they close enough for government work? There's a similar issue when comparing strings, and the thing to understand there harkens back to this idea of an object reference. Remember, variables that are declared to be of a type of class are in fact object references. And that object reference is actually just a 32 or 64-bit word that references where the thing is. And that's true of especially of strings. And there's a bit of a gotcha there, which is why, again, the double equals isn't used here. If you're coming from JavaScript had this triple equals thing that kind of overcame some of that. Java does not have that. So what I hope, one of the things I hope you're starting to realize is that even though Java and JavaScript have the same Java name in them, they are wildly different languages and really have no relationship whatsoever one to the other. And then we'll look at the while loop and using nested while loops. Okay, So some key situations, so we have comparing floating point values for equality, comparing characters. Now, characters, remember, are these they're atomic things. And so you can compare characters. And the thing about comparing strings, though, is that the strings actually have a default order to them. And it's actually not alphabetical order, it's actually lexicographic order. So if you want to compare strings and think you're doing it alphabetically, then you're actually not. And then the key to understanding all of that is the idea of comparing the contents of an object as being the same versus comparing the object references of being the same. We will see that in strings, where if I have two strings that have exactly the same characters in them, you want to think that they're equal, but they may not be, because they may be referring to different objects that happen to have the same characters. Okay, that's an important thing to understand. Okay, so integer data is very straightforward. So whether it's an int or a long, which we will use, a short, which is kind of a useless thing, which the idea of shorts, it goes back to when computers were really tiny compared with today's smartphones. And so they wanted to squeeze space out. And so defining something to be a short, it's like if I have an integer that's just going to use a handful of values and not get into very large values, then they define these short things so it would take up less space. The problem is that with Java, the way that it implements shorts is that it implements shorts with a storage which is an int size. So if you use a Java short, you're actually not saving any space whatsoever. That's why it's kind of useless. Okay, but if I have two integers, then, and I compare them for equality like this, that's always exactly true or it's exactly false. And there's no ambiguity about that whatsoever. So 3, if I have an expression that evaluates to 3 as an int and another expression that evaluates to 3 as an int, they are exactly equal. And if the other expression evaluates to 5 or something else, then they are not equal. That is a hard and fast line. Floating point data is trickier. Okay, so when you're comparing floating point values, again, this is a mortal sin, almost akin, I mean, in some ways it's even worse than declaring public instance variables, although one could argue, but it's bad. Never use double equal is fine for ints and integer values. Never use it for floating point values. Because, see, the reason is the finite precision of digital representations. See, under the hood, a floating point value it's represented some way. Exactly how, I mean, there are big endians and little, I mean, there are all kinds of different ways. We don't have to be concerned about that. But we can have two floating point values that ought to be equal, but they are considered to be equal only if the underlying binary representations match exactly. That's sort of the key here, exactly. And it's very easy to have computations that result in slightly different, these slight differences have to do with the finite precision of the digital computer. And they may be irrelevant and you want them to be equal, but you typically have to consider them to be, quote, close enough. And that may be kind of abstract. So in order to make that a little more concrete, if you update your class code repo. Here is the situation. So here's my target. My target is going to be 1. Okay, floating a double 1. Now I'm going to create a 1 in another way. I'm going to call this attempt because it's going to be an attempt, and I'm going to add 0.1 10 times. If you count this, it's 10 times. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I did it this way because we haven't introduced the for loop yet. But this, what I'm doing is I'm just adding 0.1 10 times. So these ought to be equal. Mathematically, if I take 0.1 and add it 10 times, I get 1. My target is set to be 1. All right, but here I'm saying, are they equal? And when I run this, you will see they are not equal. Why aren't they equal? Because adding 0.1 10 times produces a little bit of difference way out. I'm not sure how far out it is. I could probably try to find it, but that isn't the point. The point is these values should be equal, but they are not. Say, well, how, if I have two different ways of computing a floating point number and I want to say, are they equal or not? That is a question that you shouldn't be asking. You should be asking, are they close enough? Are they close enough for government work? Okay, what is government work? Government work is a certain tolerance. So what you should do is I should say, well, in this particular case, I'm saying if I have two values that are within 10 to the minus 10, then I will consider them to be equal. And so instead of saying, are they equal? You want to say, are they within this tolerance of each other? And how do I do that? I take the absolute value of the difference and I say, is that less than the tolerance? And if that's less than the tolerance, then I will consider that to be true. So in the second part where I do it the right way, then in fact, they are within 10 to the minus 10 of each other. And for a particular application, it may be 10 to the minus 20, it may be 10 to the minus 5, whatever it is. In a particular application, you need to specify what that tolerance should be. And that tolerance is how close do two floating point values have to be before you will consider them to be equal. Because when you do computation, just a simple enough computation like this, adding 0.1 10 times, it can't, I mean, it can't get too much simpler. And they still come up with a quantity which is not exactly equal to what I want here. And it may be that representing this may be the one that's off. You just don't know. Okay, so that's why floating point values should never be done with a double equal. So here the 1, 2, 3, 4, 5. So this was 10 to the minus 6. So again, what is the tolerance you want? Then close enough. Okay, so now let's look at characters a little bit. Remember, we have the Unicode character set, which was an extension of the old ASCII character set. And the way that it's represented is that each character has a particular numeric value. And so you can say one character is going to be less than the other, or greater than the other, or equal to the other, if depending on whether their Unicode number is greater than, less than, or equal to. So in particular, oops, the plus, say, is less than the character J because it comes before it in the Unicode character set. Now, for most of higher level programming, we don't need to necessarily be quite at that level. Every now and then we have to delve deeply into that if we're manipulating strings a lot. But the reason why this is important is to understand how lexicographic ordering works in, and that's the default ordering of strings in Java. Okay, so, I mean, in particular, most of what we're going to be dealing with have to do with numbers and letters. And the important thing to notice here is that all of the capital letters come before all of the lowercase letters. And so what that means in particular is that the capital Z is less than the lowercase a. So that's why alphabetic ordering is not quite what is being done. It is lexicographic ordering. Okay, so if you have strings, you might think if I have two strings that have exactly the same characters in them, and I want to say, are these the same string? You, again, should not be using the double equals. Should not be using the double equals. You should be using the equals method in strings. So here's how we do it. If I have, say, name1 and name2, if these are both strings, I can say, this will be true if they have the same characters and false if they don't. It also has something called the Compareto method that will, let's see. Okay, so let me see. Let me open this up just to kind of show you how this works. Because remember, strings are object. That's something you really want to keep in mind here. So, and Java's optimizing compiler does some tricks that can make this look a little wonky because, but let's take a look at this. So here's our target. So we have a string here, and then I'm going to take two pieces. And then when I concatenate them together, I actually should produce the same string. Okay, but here's what happens if I do this. Okay, so look, result and target they have exactly the same characters. And so if I try to do a double equal though, and I run it, we notice that it comes up false. Okay, so here's how to understand that. Remember, these are object references. So target is referring to an object, a string object, whose characters happen to be this. When I create this string, this is now pointing to a different object, whose character, a different string object, whose characters happen to be exactly the same as the string characters, the characters in this first string. When you compare double equals for two object references, it will be true if they refer to the same object and false if they don't, regardless of what the contents are. So if you remember that, then you'll be able to figure out all of this. So that's the thing you should remember. So I'll say it again. Double equals for object references is going to be true if the two object references refer to the same object, and it's going to be false otherwise. So for example, in this one, supposing now, if I do this, then I'll just, Now this is true because these are now pointing to the same object. See, so now it comes up true. See, so the thing to remember, and this is true of all object references. Double equal is true if they refer to the same object. It's false if they don't, regardless of what the contents are. Okay, so we'll circle back to this. And now the interesting thing about strings, and we're going to be talking about sorting and using sorted containers at some point. And the way that that's done, or a way that that's done, is that this Compareto method is what's being used. So in this particular case, strings have the Compareto method. And the Compareto method returns a positive value, a negative value, or 0, depending on if they are equal. That is, in the case of strings, if they contain the same characters, then instead of saying equal, if I say compare to, it'll return 0. Now, if the first one is less than the second one, it will return a negative value. And it will, if it's greater than, it will return a positive value. So now what does it mean if two strings, if one string is less than another? Well, that's what this lexicographic ordering has to do. It gets back to that Unicode idea. So with this Unicode business, if it basically takes each string and it looks at the characters one at a time. And when it encounters a difference in the characters, it then compares the Unicode quantity to decide whether it's greater than or less than. So, and so it's kind of alphabetical, but it's not strictly alphabetical when you have upper and lowercase. So, for example, great comes before fantastic because it looks character by character. So it looks at G compared to F, and it says, I got one. G is less than F. Why? Because all uppercase letters come before all lowercase letters. Shorter strings come before longer strings. And so book comes before bookcase. So what it does is, it looks, okay, lowercase b, move to the next, lowercase o, lowercase o, lowercase o, lowercase o, lowercase k. Now, nothing but something here, even if there's something, then that means that this is less than that. Let's come back to this. And going back to what we had here, and just to illustrate this, we had one string ZZ top, and the other is ABBA. And so the compare to produces an int, which is either going to be 0, less than, or 0, or greater than 0. And so we see that in this case, compare is less than 0, and that means ZZ top comes before ABBA. Now, of course, if we made this uppercase, it would be the other way. Why? Because it looks capital Z, capital A comes before capital Z. Whereas if it's lowercase like this, then capital Z comes before lowercase a. Okay, again, this bears understanding. If we have object references. It returns true if they're, well, they say alias. Basically, if remember, that's just a fancy way of saying that the two object references are both referring to the same object. Now, every object has an equals method. But the default double equals, the default equals method is the same as the double equals. In other words, if I don't do anything, then the equals method will be the same as the double equals method. Sometimes that's okay, sometimes that's not what we want. In the case of the string class, what happened is that they redefined the equals method in the string class to compare the characters. So when you write a class and you want to say that two objects are essentially equal, then you can redefine the equals method to return true under the conditions that are appropriate. So for example, if you remember the die class, I can say that two die instances are equals if they have the same number of dots showing. Remember the playing card class. I can say two playing card instances are equal if they have the same suit and the same value. But if I don't do that, as the playing card class as it currently exists, that if I can create one playing card instance, say the Jack of Clubs, create another playing card instance that's also the Jack of Clubs. If I say equal, are they equal? It will say no. Why? Because they are different objects. Okay, so that's comparing data. Now, repetition statements. Basically, there are three. There's the while, the do while, and the for loop. So we're going to talk about the do while and the for loop next class. You've already kind of seen both of those in code that I've given you. You've no doubt encountered those in your previous languages, but since we haven't formally presented those yet, I was just giving those. Okay, so sometimes these are called loops. In the first programming language I learned was something called Fortran, which I wrote using punch cards. And the only loop they had was something called a do loop. And that was the moral equivalent of the for loop. Okay, so just like conditional statement, we control these with Boolean expressions. And so here's how the while works. So the while says, while a particular condition is true, the statement keeps getting executed. When they say statement, again, as you should always put the curly braces in, because if you don't put the curly braces in, then the while will only execute the very next statement. When you put the curly braces in, it takes a block of statements and it turns it into one for semantic purposes. So when you're executing the code, again, in contrast to the previous experience of starting at the top of the page and just working your way to the bottom, that same logic applies when you call a method. So all of this is taking place within a method. You know, you start at the top of the method and you work your way to the bottom of the method. And so if there's something that needs to be executed in a continuous way until a particular condition becomes true, false. So as long as the condition is true, the statement gets executed. And so the way that you want to construct these is such that within your statements, you are doing things to change the condition. If the condition is true when you start and you never change the truthiness of that condition, it will continue forever. So you basically keep going. And sort of the flow chart version of this is we evaluate the condition. If it's true, we execute the statement and reinitiate. And we just basically keep going on this loop until at some point it becomes false, and then we keep executing. Okay, so here's an example. And so I want to execute something, let's say 5 times. So I have an int that's a count. I'll initialize it to 1. And my statement is while count is less than or equal to 5, then I'm going to print it out, but then increment the count. And just as kind of a stylistic thing, having the plus plus on one line is sort of okay. I personally prefer this, something that looks something like this. Slight personal preference. If you like the plus plus, I'm fine with that. But, or I mean, I will tolerate that. But for me, it just these plus plus and minus unary operators are so potentially dangerous that you never want to use them in a bigger expression. Using them only in for loops and only by themselves on one line is sort of okay, and I still prefer this. Okay, so let's look at this. Count is 1. Count, is it less than or equal to 5? Yes, it is. It executes that, prints 1. And increments count. Now count is 2. Is 2 less than or equal to 5? Yep. Print 2. Now count is 3. Is 3 less than or equal to 5? 4. 5 is less than or equal to 5, so it'll print 5, and then finally when it gets to 6, it becomes false and you execute it. Now, if we were to initialize count to 6, none of this would ever happen. So the key difference between a while and then the do while that we'll talk about tomorrow is that a while loop will be executed 0 or more times. It'll be executed 0 times if the initial condition is false. It will be executed 1 or more times if the initial condition is true. Now, one way to kind of stop a loop is something that they call a sentinel value. And that's a useful thing, but the book has an example that is not ideal. So I want to show you a better example. Where is it? Okay, there's a little package here where I have. Okay, so what the book's example, let's see, let's look at the book's example and I'll show you what my problem is with it. Okay, so we're going to enter, the idea is we're going to enter a bunch of integers, and the object of this is to produce the average of these integers. Okay, so they set up a scanner that we've been using, and then we enter an integer, and then they're using a sentinel value of 0 to quit. And okay, so they get the value, and basically while the value is not equal to 0, they'll increment the count, they'll increment the sum, and then keep doing that until you enter a 0. Now, can anybody think of why that might be problematic? Anybody?
Is it because there's like infinitely more other numbers than 0, so you never actually have a guarantee that someone's going to enter a 0?
Well, that's that. Yeah, that's kind of a possibility. What if I wanted to take the average of numbers that included 0? How would I be able to do that using this program?
You can't.
Exactly. So that's a bit of a problem. Yeah. I mean, you're right. Yeah, there's no guarantee that the user's going to ever enter the ending value. But presumably, if I'm a user and I want to say, okay, I want to find the average of these different values, then presumably at some point I'm going to say, okay, these are the only values that I have. But if my data includes zeros, then I'm screwed. Okay, so right, so a better design, this is to have the central value not be a legal input. In other words, the problem is that 0 is not a good central value because it could be a legitimate value. Okay, so what is the alternative? The alternative is to have a sentinel value that cannot be legitimate no matter what. Now, so a solution, again, this isn't a perfect solution, but this is a better solution. So again, we have a count and we have sum. So my signal to quit is if the user enters the string Q. Okay. And so now I have another string that says this is to say whether the user quit. And so my condition is that the user quits string is not equal to my quit string. Okay, so now I'm saying, give me an X integer, enter Q to quit. So now I can say, well, if the next thing is an integer, then I do all that. However, if it's not an integer, then I'm going to look at what that is. And if it's not, okay, so it hasn't entered an integer. And if it's not equal to quit, then I'm saying, hey, you got to either enter an integer or a Q. But if it is Q, then when it circles back to the while test, now they're going to be equal. And then this is another little gotcha on the other one. What if you have no data whatsoever? What if you quit right away? Well, okay. So first, what happens if I quit right away? If I say quit, then I say no data entered. Now, the thing is, if I don't do that, let's just make this always the case. If I run this again and I quit right away, then my average is not a number. Why? Because it's 0 over 0. Okay. So instead, if I want, now I can enter a 0 as a possible value. And then when I finally quit, then I get whatever that average was. Okay, so the lesson is that your sentinel should not be a legal input value. When you're reading this is especially important when you're reading data from a file, because sometimes you'll get data, something that ought to be a number, but is some other character that indicates that it's like a missing value. And as we've seen, the NaN. Okay, so it's generally a good idea to validate your input. So they have, let's say, they have a win percentage. And the idea here is that, okay, we have a certain number of games that we've played, and we want to find out what our winning percentage is. And so the way they do that, and this one is a little bit better. So we have again a final int here that this is how many games there were. This is gonna be how many were won. This is what the ratio is, and we're gonna say how many, enter the number of games that you won. Now here's the problem. If you enter like -3, you can't win -3 games. Or if you enter more games than were played, then those are bad values. So how do you check for that? Again, with the while loop here, you keep nagging the user until they enter a correct, a valid number. So what are invalid numbers? Less than 0 or greater than the number of games played. And so basically you get stuck in this loop here until you enter a value that's legitimate. Now, the other thing is if you want to be good to your users, especially if you're the user, this is not a good input because it's not making, you want to make it as clear as possible to the user what you expect. If you keep saying, have you ever gotten stuck in some application or a web form or something where it's just not accepting what you have, but it's not telling you what it wants? I know that sometimes happens here. It's like, what's wrong? Well, if you don't know, I'm not going to tell you. Well, if we're entering stuff and you're not happy, you should, if you're writing the application, you should be telling it. So, okay, so here, yeah, the object is to kind of keep the bad data out. So here's my reworking with it a little bit. Mostly just to say, hey, here's what you want. So when we run this, like if I enter a bad value, I'm saying, okay, please enter a number between 0 and 12. And as long as I keep doing that. So right now I'm stuck in this loop here. And then when I finally do it, we get the win percentage. So yeah, so basically my only complaint about this was for the from the book was that it didn't give a good user message. Okay, so you want to be careful about having an infinite loop. And it's important to test edge conditions, that is, don't assume that the user will always be, or that the data that you're processing or the conditions you're testing are always going to be absolutely correct. You want to test the accuracy. So here's an example of an infinite loop. Again, this is a nice example. So we have our count, and while the count is less than 25, we'll say, okay, here's the count, but now instead of incrementing the count, we're decrementing the count. So count's going to go 1, 0, -1, etc. And basically it's going to keep executing until it's interrupted. They say Control C, that's if we're executing it from the command line. If we're executing it from NetBeans, then there's the way to do it if you haven't found it already. So let's say for whatever, so let's say we were stuck in an infinite loop here. and I wanted to just end it. You see this little red box over here? You hit the red box and we stop. Okay, so instead of Control C, if we're running on the command line, Control C will stop it. If we're running in NetBeans, then that little red box will stop it. Okay, so nested loops. This is actually a very cute little one. So I basically kind of put that out just because it's kind of fun. And it's okay. So now notice that now we're using kind of a sentinel, which in a way is not sort of something that you'd want to be testing. So this is a good sense, even though it's a string. The idea here is that I want to find out if a particular string is a palindrome. If I have a single letter in my string, then by default, it's sort of a palindrome, I guess. But that's not something you'd ever want to test. So that's actually a decent sentinel. And then also they're using something called equals ignore case, and that'll allow you to either enter lowercase or uppercase. So what they're using here is that they have like a left starting at 0 and a right, which is the index of the last character of the string. And how do we find that? Well, strings have a method called length that says how many characters there are. But since it uses zero-based indexing, this is the index of the last letter of the string. And so this is very clever code. So this says while the character at the left is equal to the character at the right, and left is less than right, we kind of click over to the left and click to the right on left and click to the left on right. And then finally, when we exit that, if we have overstepped, if we've kind of ended before we've hit the right, then we're not a palindrome. Or if we have, then we are a palindrome. And remember, a palindrome is okay, so radar, able was I, error I saw, Elba, etc. So let's see. I know I'm a minute over, but in the code here, we have the Palindrome Tester, so we can have there, and then what's it? There's one.
You need to answer yes or no there to answer another palindrome.
Oh, yeah. Thanks, yeah. I forgot to say the yes. Okay, so next. Anyway, so well, that's there. And okay, so we're kind of out of time, but next read sections 5.5 and 5.6.